This video is for ELEC 1510 Logic Design. This is Lecture 12, Part 1 on encoders, corresponding to textbook section 4.10. Encoders are basically the opposite of a decoder. If they have 2 to the n inputs, they'll have n outputs. Decoders have n inputs and 2 to the n outputs. Basically, for an encoder, one input should be on at any given time. So any set of inputs where more than one of the inputs are on at a time is an illegal operation. The outputs will show which input is on. So basically, an encoder looks something like this. This is an 8x3 encoder where we have 8 inputs, I7 through I0, and 3 outputs, O2 through O0. When the input I0 is a 1, we output the 3 output bits corresponding to the input that was turned on. So this was I0, and we display 0, 0, 0. For I1 being on, right here, we display 0, 0, 1. And finally, for I7 being on, we display 1, 1, 1. Now, the truth table that you would have to draw in order to include all possible inputs would be enormous. So we don't actually normally define this type of function in terms of all possible inputs. And actually, just defining an encoder this way leads to very simple output functions. For the outputs, we actually just look at the set of inputs that are on to define that output, and then define the output as the sum of those inputs. So output 0 right here is on here, 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 and here. So that would be inputs I1, I3, I5, and I7. So the function for output 0 is going to be I1 or I3 or I5 or I7. If you were to actually write out the 8-dimensional K-map for this, that is the function that you would come up with as the most optimal function for output 0. Output 1 then is on here and here, so that's input 2 and 3, and on here that's input 6 and 7. So output 1 has the function input 2 or input 3 or input 6 or input 7. Then finally, output 2 is on for these 4 sets of inputs, which is input 4 or input 5 or input 6 or input 7. A priority encoder is a different version of an encoder that is probably more practical than an ordinary encoder. A priority encoder, we'll say, has n inputs. For example, we'll just say that it has inputs 0 and 3 for this example. We're going to say in a practical sense that each one of these inputs represents a priority, and they could be something like an alert. Like maybe some sort of message has arrived. So a priority 0 alert is a message that arrives but has low priority. So that would be input 0 into the system. Input 3 is a priority 3 alert, so that means a high priority alert has arrived. What the priority encoder reports at its output is the highest priority alert that has arrived. So if inputs 0, 1, 2, and 3 are all active, it's only going to report out priority 3. As soon as the system will then take care of that priority, then it will move on to the less urgent priorities. So it's always going to report the highest priority alert that's available. By doing this, you allow the system to respond to the highest priority alerts first. So basically, a priority encoder with 4 inputs has a truth table that looks like this. So let's start with the case where an alert with priority level 0 has arrived and no alerts with priority level 1, 2, or 3 have arrived. So that priority level that has arrived is reported at the output. That was level 0, which we see being reported at the output. Now, let's say that we have a case here where a priority level 1 input has occurred. There's no priority level 0 input and no priority level 2 or 3 inputs. Well, number 1 has occurred, so we're going to report out the number 1 at the outputs. Now, if both priority levels 1 and 0 have arrived, we're still going to report out the highest one that's arrived, so that's number 1. Okay, so then you can fast forward through all of this and see that for all of these inputs where priority level 3 inputs have arrived, we're going to report out 3, no matter what is going on with the lower priority inputs. All right, so we're also missing a scenario in here, which is when no inputs have arrived. And so that's taken care of by an additional output called a valid bit. So V stands for valid. If the valid bit is a 0, that means that no inputs have arrived. If the valid bit is a 1 in all of these scenarios, that means that something has arrived and you need to start taking care of one of those alerts. So for inputs equal to 0, 0, 0, 0, the outputs don't matter because we're just going to say that if the valid bit is 0, nothing has arrived. This could perhaps simplify the output functions a little bit. We can rewrite this truth table in a more simplified manner, like this, where the input condition of all zeros leads to an output condition of don't care, and valid bit being 0. Then in the next row, if we have a priority level 0 message that has occurred, the valid bit is a 1, meaning that there's a message that you have to take care of, and the output bits are 0 and 0, meaning it's priority level 0. For the next set of inputs, a level 1 alert has occurred, and we don't care whether or not a level 0 input has occurred. And then we report out valid bit being 1 and the output being that a level 1 input has occurred. Then we continue that same theme for the rest of the inputs. For a level 2 message that has occurred, we don't care if a level 1 or level 0 has occurred. We report a valid bit being 1 and the output being 2. And then same thing for input 3 having occurred. We don't care about the lower level inputs. We report out 3 and a valid bit being 1. So now the output functions for the valid bit, output 1 and output 2 are as follows. The valid bit is going to be I0 or I1 or I2 or I3. Basically, if any input has occurred, the valid bit is a 1. Output sub 1, that's I3 or I1, I2 prime. And output 2 is I3 or I2. So that's basically how a priority encoder works. There's a homework question that asks you to analyze the priority encoder circuit and design that circuit in Verilog. So encoders are not quite as important as decoders. They work for specific purposes, but they can't be used to implement general functions like decoders can.